Let's look at number 17. I give you Cu2SO4 and lithium, Li. What you should do is recognize the fact that this is a single replacement reaction. So what actually happens is Li is going to go in, and let me draw this properly. Li is going to go in and it's going to kick out Cu, because positives kick out positives. All right, so Li and SO4 are going to make a brand new compound, which creates the question, what is the charge of SO4? Well, I kind of drew over it right here, but if you see that 2 right there, you can uncross your charges and see that that is your charge of SO4. So SO4 has a charge of -2. Okay, don't mess with the 4 from SO4 because that's one entity, but if you notice there isn't a subscript for SO4, which means in this problem my charge of Cu is +1. Okay, but that doesn't really matter to me right now. I'm creating a compound between Li and SO4. So Li has a +1 charge, which is awesome. That's what I wanted. And SO4 has a 2- charge. So when I'm done crossing my charges, okay, that 2 becomes a subscript for the Li, the 1 becomes a subscript for SO4, so this becomes Li2SO4. Okay? And my other product is Cu, which was kicked out. And Cu is just going to be by itself. No charge, no nothing. It's all by itself. Now, this says, what do you need to do in order to make sure you follow law of conservation of matter? Law of conservation of matter. Matter cannot be created nor destroyed. You need to balance, guys. Whenever I say that, balance. Law of conservation is just balancing. So let's go ahead and balance this. Okay, I've got 2 Li's right here. I've got 2 Li's right here. So I put a 2 there because there was only 1 before. I've got 1 SO4 here, 1 SO4 here. I'm good with that. I've got 2 Cu's here. I've got 2 Cu's here. Do not use subscripts. You cannot balance using subscripts. You can only balance using coefficients. Now it says, write the states of matter behind the product for the reaction above. Remember, the only time it's going to be liquid is if it's a pure substance. You guys will never see that in a reaction. So the only states of matter you will have to write in are either solid, aqueous, or gas. Okay? So whenever you see a metal all by itself, it's going to be a solid. Okay? Think of everyday metals that you have. Obviously, it's not going to be any sort of liquid or a gas. Any ionic compound, which Li2SO4 is always going to be aqueous. Okay, an example of a gas, for example, I'm going to write it up here, would be like if I gave you H2. That would be a gas, but I didn't give that to you in this problem. Okay, last thing, right? Oh, convert 54 centimeters to kilometers. So I'm going to do that really quickly. I have 54 centimeters. I want to convert it to kilometers, so I'm going to take 2 steps, crisscross swoosh. Okay, I'm going to put centimeters in the bottom and meters up top. I'm going to first go to meters because I don't really know the relationship between kilometers and centimeters. Okay, and if I do, I don't really want to think about it. Okay, so I first go to my base unit, which is meters. Then I'm going to crisscross swoosh again. Now, I'm in meters. I don't want to be in meters. I want to be in kilometers. So I'm going to put meters in the bottom, and I'm going to put kilometers up top. Now, all I have to do, I've taken care of all my units. Now I just have to put the relationships. So what I ask myself is the following. Which is bigger, meters or centimeters? And you should say, well, yeah, of course, meters are. So a 1. And how many centimeters are in a meter? Well, they're 100. And guys, on your final, I'm not going to ask random ones, but stuff like centimeters, kilometers, decimeters, nanometers, stuff like that, yeah, you will have to know those. Okay? Now, you should ask yourself the question, which one's bigger, kilometers or meters? And, well, kilometers are bigger, so I'm going to put a 1 in front of kilometers. How many meters in a kilometer? There are 1,000. So what you're going to do is you're going to take 54, and since this is in the denominator, you're going to divide 54 by 100 and then by 1,000. And what you get is 5.4 times 10 to the negative, can't really see it, 4th kilometers. And so those are going to be your units. Another way of writing that is just 0.000, so 3 zeros. And I'll write it right here. 0.00054 kilometers. 2 different perfectly fine answers. Okay, I need to do is determine the number of valence electrons. So for nitrogen, if you look at your periodic table and count across, group 1 being having one valence electron, group 2 having 2, the skipping over that middle group, right, and the group with Al having 3, then 4, you'll find that nitrogen has a total of 5 valence electrons. So nitrogen has 5, okay, and then iodine, if you count in a similar way to find the valence electrons, you'll find that iodine has 7. Well, that's great, but you have 3 iodides total. So what you'll need to do is multiply 7 times 3, which is 21. So when you do that addition, what you'll find is you have 26 valence electrons. So when I draw my Lewis dot structure, I need N in the center, and I have 3 I's. So whenever I see 3, I'm just going to draw it like this, just to be safe. So I'm going to put I here, an I here, and an I here. Okay, now I'm going to fill in with all of the valence electrons. Remember, each element needs to have 8 valence electrons around it. Okay, so I right now only has 2 because this line represents 2 valence electrons. So now it's got 4, 6, and 8. This has 4, 6, and now 8. And this has 4, 6, and now 8. Okay, and if you notice, everyone's happy except for nitrogen. Nitrogen now has 2, 4, 6, and so I need to put 2 on top. My last thing that I need to do, guys, is make sure I only use 26 valence electrons, because if I used any more than 26 valence electrons, I'm going to have to start double bonding, which hopefully I don't have to do. So let's count. 2, 4, 6, 8. So I have 2 here, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and I'm safe. Okay, if you notice on your chart, this is going to be, the shape is trigonal pyramidal. The difference between trigonal pyramidal and trigonal planar is that, pyramidal, I'll just write it pyramid, is that planar would just have 3 things bound to it and it wouldn't have that lone pair of electrons on top. Okay, when we're talking about whether the bonds are polar or nonpolar, specifically what we're talking about is looking at just one bond. If you have the same element on either side, which in this case you don't actually, but if you did, then it would be nonpolar. But if you do not have the same element on either side of a bond, then it's going to be a polar bond, which we have here. Now, the last thing you need to think about, if you look at your molecule as a whole and you imagine a tug of war, so iodide's pulling this way, iodide's pulling this way, and iodide's pulling this way. If nitrogen were not to move in that tug of war, okay, then your molecule would be nonpolar. But since there isn't anyone pulling up this way, since there isn't an I here, and your lone pair of electrons don't help at all in that tug of war, nitrogen's going to be forced downwards because there's no opposing upwards force. Okay? Therefore, if your central atom were to move, then it's polar. If it were not, meaning your forces are balanced completely, then it's nonpolar. So in this case, it's polar. All right, let's look at another one. S. S has 6 valence electrons. H has 1, but there are 2 H's, so it has a total of 2. Therefore, SH2 has 8 valence electrons. So when I draw this, I'm going to have my S and my H's. Okay. Remember, H, don't ever put any dots on H. H just needs those 2 valence electrons and then it's happy. So it's got 2 here and this one has 2 here and it's happy. Now S is not. S only has 4 valence electrons and it needs a total of 8. So I'm going to draw 4. So this is 2, 4, 6 and then this makes 8. Now notice I didn't put 2 on the bottom because I don't want to confuse you. As soon as you have lone pairs of electrons on your central atom, you will no longer have a linear compound. Okay, so I drew it like this because these electrons force that hydrogen downwards into a shape that we call bent. Now, let's look at our bonds. That's when you just look down one single bond, so let's look here. Remember, if they're different, then it's polar. If they're the same, then it's nonpolar. Well, these are totally different, therefore, it's going to be polar. All right, now, H is pulling down this way, H is pulling down this way, but there's no 2 other things pulling up that way at all. Instead, they're just those lone pairs of electrons. Therefore, this is also going to be polar. Okay, let's look at this last one, I2. I has a 7 valence electrons, and since there are 2 of them, it's 7 times 2. Therefore, we have 14 valence electrons. So I'm going to draw my I bound together. Then your next step is to make sure they're happy. Well, I right now has 2 valence electrons, so I need to add 4, 6, 8, 2, 4, 6, 8. Now it's happy. Let's see how many I've used and make sure I haven't gone over that 14 limit. 2, 4, 6, 8, 10, 12, 14. Perfect. Now, if for example I were only allowed to have 12 valence electrons, like what we saw with oxygen, that's when you need to double bond it and get rid of these 2 electrons and these 2 electrons right there. Okay, so go back in your notes and see that if you don't remember that. Now, in this case, since you just have 2 things connected to each other, that is linear. If you look along your bond, and this is just one bond, you have the same element on either side, which makes it non-polar, finally. And I is going to be pulling with pretty much the same force that the other I is going to be pulling on, like identical twins basically. So therefore, no one's going to be going anywhere. Therefore, it's going to be non-polar. All right, let's look really quickly at this table. This is going to be worth quite a bit of points on your test, so I want to make sure you guys understand it. So let's look at Ca quickly. All right, if you look at your periodic table, what it looks like is the following. You have, for each element, I'll show you for Ca, okay, you've got a box, and then you've got a number on top, so 20 for Ca, then its symbol, Ca, and then you have another number on bottom, which in this case is 40.08. Okay, so what you need to do, 20 is the atomic number. This is the mass number, which you'll have to round to a whole number. Okay, so 40 is the mass number of Ca. Okay. Protons. Protons are the exact same thing as saying your atomic number. So it's right on top, guys. So I give that to you. Now, your mass number is your number of protons plus your number of neutrons. Okay, so if I have 40 equals 20 plus what, right? Because mass number equals protons plus neutrons. Therefore, if I have 20 protons, how many neutrons would I have to have a mass number of 40? Well, 20. Awesome. Okay. If I have 20 pluses, right, 20 protons, and 18 electrons, what that tells me is I have 2 more protons than electrons, which means my ionic charge is going to be 2 plus. Okay, let's keep going. If I have 16 protons, I first have to find what element that is, and what I find is that it's sulfur. Okay, the mass number of sulfur, well, the average atomic mass of sulfur is 32.06. You round that, and that becomes just 32. Alrighty, so mass number is 32, number of protons is 16. Remember, protons plus neutrons equals your mass number, therefore my number of neutrons is just 16. Okay, important thing. Your protons and neutrons are not always identical. This is just a weird case where they are. Okay, so don't assume that because that's a very bad assumption. Okay, now I have 16 protons and I know my ionic charge is -2. Okay, which means I have 2 more electrons than I do protons, since electrons are negatively charged. So if I have 2 more electrons than protons, I've got to have 18 electrons. All right, keep going. Mass number of 27. So you've got to search through this and find whatever element has a mass number of 27. And what you'll find is that aluminum has an average atomic mass of 26.982, which rounds to 27. So there we go. I found that aluminum is my element. Okay, the number of protons of aluminum is 13. That's its mass number. That's its atomic number. Okay, if it has 13 protons, how many neutrons does it need to have a mass number of 27? 14, right? Because 13 plus 14 is 27. Now, its ionic charge is +3, which means I have to have 3 more protons, since protons have a positive charge, than electrons. So 3 more protons than electrons, that means I would have 10 electrons, right? Now I have 3 more protons than electrons. Cool. Boron. What's my mass number of boron? My mass number of boron is, well, my average atomic mass is 10.81, which rounded is 11. A lot of people made that mistake, okay? My atomic number is 5, which is my number of protons. So if I have 5 protons and my mass number is 11, that means I have 6 neutrons. Okay? 5 protons, only 2 electrons, that means I have 3 more protons than electrons, which means I have a +3 charge.